very happy to be here today to report back to you about the results from the Black Hole Working Group from the past year. And of course, I'm here just as a representative of a very large group, their contributions from a huge number of people to this talk, some of whom are already here today. My co-leaders are Lars Hörnquist, Greg Bryan, and Brian Terrazas. So where does the Black Hole Working Group fit into this learning the universe picture? So I've titled the talk The Black Hole Galaxy Connection, and it already gives the hint that black holes are all about learning the interconnected universe. So we've got here the feedback from the black holes that will couple to the gas in the galaxy, and then, as we already heard in the previous talk, affect large-scale cosmic structure. And we can see this large-scale impact beautifully in this video from the Illustrious collaboration, where you've got the cosmic web, and then you've got the feedback from the supermassive black holes driving these large bubbles and affecting structure on megaparsec scales. So here's just a quick revision slide about the supermassive black hole galaxy connection in a nutshell. So most large galaxies, if not all galaxies, host a supermassive black hole at their center. And when these supermassive black holes are actively accreting the surrounding gas, they're often referred to as active galactic nuclei, as they release huge amounts of energy as they devour the gas surrounding them. And this energy then comes in the forms of winds, jets, and radiation. And it's a very exciting time to be working on supermassive black holes, as these exciting observational facilities that I've shown here on the left-hand side have ushered in a new era for supermassive black hole science. And I'm just going to highlight some results. So one thing is that JWST has found a surprising number of AGN in the early universe. And a lot of these AGN are inferred to be powered by seemingly overmassive black holes. The other exciting strand is that a couple of years ago, there was the first evidence for the detection of low-frequency gravitational waves. So gravitational waves in the supermassive regime, rather than the stellar mass or intermediate mass regime that is accessible by LIGO. And these two strands are now also starting to come together with the first hints at high redshift dual AGN. And these exciting discoveries really form the backdrop for 4 key challenges for our working group. The first one being the origin of supermassive black holes, so how do supermassive black holes form in the early universe? The second one being the dynamics of supermassive black holes, so the black hole orbits. And this is particularly important for understanding supermassive black hole mergers and that PTA signal, as well as, of course, looking towards LISA, which for the first time will detect individual supermassive black hole mergers. The third challenge is the growth of supermassive black holes, so understanding how the gas accretion process works in detail, which then, of course, in turn connects to the fourth challenge, which is the interaction between black holes and their host galaxies, collectively known as feedback. And the reasons why these are called challenges and not just the plans for the Black Hole Working Group is because modeling all of this is notoriously difficult. And this is mostly due to the multi-scale nature of the supermassive black hole galaxy coevolution. So if we were to try and simulate the supermassive black hole galaxy connection ab initio, we would have to start at the event horizon, which for the supermassive black hole at the center of our Milky Way roughly corresponds to microparsec scales. We would then need to model the accretion disk that forms around the black hole, which is where all of these crucial feedback processes originate from, so the jets, the winds, and the radiation. This happens typically at scales of tens of milliparsecs. We then want to see how this feedback couples to the center of the galaxy, possibly also investigate the role of binary supermassive black holes. This happens at scales of tens of parsecs. We then want to see how this feedback drives these beautiful large-scale outflows that we saw in the video, which are at least at scales of tens of kiloparsecs. And then ultimately, we want to investigate how these outflows couple to the inflows from large-scale cosmic structure and how they affect large-scale cosmic structure, as we heard in the last talk. For this, we're talking about scales of at least tens of megaparsecs. So if we want all of this in one simulation, we would need to span at least 14 orders of magnitude. Now, if you want to run such a simulation from shortly after the Big Bang to the present-day universe and incorporate all of these scales, that is computationally completely infeasible and will remain so for the foreseeable future. So this means there's always a compromise involved. And there are two main compromises, and our working group has followed both of these approaches. The first approach is that you say, okay, let's just focus on one single galaxy and resolve this galaxy really well, and within that galaxy push all the way down close to the event horizon and really model this AGN feedback process in detail. This is, of course, physically the most faithful approach. However, as you know, we are the learning the universe and not the learning the galaxy collaboration. So this is why, unfortunately, we cannot throw all of this out. We still care about cosmic large-scale structure. So this is where the second compromise comes in. We're saying, okay, I'm still going to have my large volumes, but this means I'm going to lose the small scales. And all of this will then have to be encapsulated in a subgrid model. And this is, of course, another approach that we have been actively pursuing. So I've listed here some of the recent papers from the past year since the last annual collaboration meeting. I will now not read out these links to you, but rather I want to present these results to you according to the 4 themes or challenges that we've identified. So starting off first with the first challenge of black hole formation. So for the birth of supermassive black holes, there are 3 broad scenarios. The first one being that they could stem from primordial stars, which would result in light seeds of approximately 100 solar masses. The second one being that they could form from the direct collapse of gigantic gas clouds. This would result in so-called heavy seeds of typically 10 to the 5 solar masses. Last but not least, another channel is the collapse of dense star clusters. These would be the intermediate mass seeds, typically perhaps around 1,000 solar masses. Now, Akland, part of the Black Hole Working Group, has implemented all of these different seeding channels spanning from light to heavy seeds and analyzed the impact of these seeding choices in his Brahma simulations. So these are one of the largest systematic studies to date to predict the black hole seeding signatures across cosmic time. And I'm showing just here some of the papers from the past year where Akland has investigated the signatures on the local universe black hole occupation fraction, on the luminosity functions, on the scaling relations, as well as on the gravitational wave event rates. As I mentioned, though, there's a new kid on the block, JWST. So Akland has been actively working on using these latest detections of the high redshift black holes to his advantage. But these high redshift black holes might likely live in rare regions and really be a kind of tip of the iceberg scenario. And to discover these kind of black holes, the Brahma volumes are really too small, which is why Akland now, with the new LTU models, is running these Brahma-constrained simulations, exploring different seeding, accretion, and feedback models. And it really does seem like the more lenient accretion variant is required to match anything close to what has been observed by JWST, assuming that these mass estimates are reliable. On the topic of JWST, another thing that we've been worrying about in the context of black hole formation are the survey selection functions. For this, in collaboration with several major observational teams, we've developed tools that allow us to select the black holes in the observations in accordance to what would be detectable with different JWST survey exposures and grading choices. And with that, we have filtered our simulated populations and also, again, tested different seed masses. So here on the right-hand side, you've got simulations with heavy seeds, so in blue and purple. And on the left-hand side, in green and orange, you've got simulations that have implemented light seeds. And the top row shows you a fiducial cosmological model, whereas the bottom row is one, again, where accretion is boosted and super Eddington accretion is permitted. So the Eddington limit is lifted for these simulations. Interestingly, if you look at the heavy seeds and take into account that selection function, then these choices actually don't matter. just because of how the selection function picks out the brightest and also the most massive black holes so that you can detect the broad line. With the heavier seeds, you would always automatically retrieve this overmassive population. This isn't true for the light seeds, which really struggle to grow with the fiducial models. However, with the boosted accretion and super Eddington, at least at redshift 4, this light seed scenario could also be a plausible explanation, although as we push to higher and higher redshifts, this gets increasingly difficult. And it should be emphasized that here the light seeds operate under extremely generous assumptions, because with the simulations that I'm showing here, they're being repositioned to the potential minimum. And they might likely, because of the nature of low-mass seeds, actually be wandering in the galaxy, which could inhibit their accretion further. And this nicely brings me to the second challenge that we need to worry about, the black hole dynamics. So in cosmological simulations, black holes are modeled as collisionless particles. And this can pose issues because in many situations, the black hole mass is similar to the dark matter mass and the stellar mass, if not smaller. And in this case, from the numerical perspective, dynamical effects will not be physically represented. So for example, dynamical friction will be under-resolved. And to avoid this, cosmological simulations have generally used this repositioning scheme that I just mentioned, where the black holes are automatically dragged towards the potential minimum of their host halo. However, this can lead to various artifacts. So this is a list that Lars compiled last year that I stole. So one of them is the black holes could be removed from their satellite galaxies. Of course, if you keep dragging black holes to the center, you're going to get incorrect orbits, especially then also for binary supermassive black holes, and you're going to merge them too early. So you're going to enhance your merger rates. This will also, as a corollary, lead to incorrect accretion rates. And of course, this putative population of wandering black holes you're not going to have by definition. And there have been various attempts to treat this unresolved dynamical friction. I've listed some references here. And actually, this last one, the Ma et al. 2023 scheme, has also been implemented by Ackland in his early universe simulations to fold into these tests. But we have also, within the working group, implemented an LTU dynamical friction model. This is led here by Anna Janina. And this model is calibrated and inspired by the highly accurate post-Newtonian CATU code. And on the top here, you can see a 10 to the 9 solar mass black hole on an eccentric orbit sinking within the halo. And on the bottom panel, you have a 10 to the 6 solar mass black hole. And the black line here shows you the analytical estimate, and the dashed line, the CATU implementation. This model so far has, in this publication, is only for idealized simulations, but it's now being deployed and tested in large-scale cosmological simulations so that we can also implement this for future cosmological runs. On the topic of dynamics, Laura Blecker and her group have also been working on taking this even further and modeling triple supermassive black hole systems. And this is really interesting because they showed that massive major mergers, especially at low redshift, are highly likely to be facilitated by these triple interactions. And it might even be that they're also more relevant at higher redshift, but that this is artificially suppressed and illustrious because you don't have these lower mass seed models. So again, this would be something that could be really interesting to revisit with the Brahma simulations. Okay, we've already covered 2 challenges. It's going quite well time-wise. Let's go and move to challenge number 3, the black hole growth. Now, this is a chunky challenge, so I'm going to give you a bit of an overview, or a roadmap through this third challenge. So first, I'm going to review with you the traditional approach that has been taken in cosmological models, the Bondi accretion model. Then we're going to look at some models that go beyond Bondi, including torque-limited accretion and dynamical models. And lastly, I'm going to present a generalized scheme, the so-called unified accretion disk model. So most cosmological simulations on the market use the spherically symmetric Bondi accretion scheme to model supermassive black hole growth via accretion. For the Bondi calculation to be accurate, you require really that the fluid has to be resolved at the Bondi radius, which is where you switch to this freefall type solution that you can see here in the image. And that Bondi radius is typically 5 to 5,000 parsecs for supermassive black holes. So this is already a lot better than microparsec, what you needed if you want to do it all ab initio, incorporate the event horizon, etc. But it should be said that even that Bondi radius is often not resolved in cosmological simulations. And there are various other caveats with this scheme. So various simplifying assumptions that go into the Bondi derivation that in the galactic context typically do not hold. So first and foremost, of course, the spherical symmetry assumption is often broken, especially in disk galaxies, where we know that rotation and angular momentum transport are crucial. And of course, also once you have AGN feedback and drive these outflows, this is another factor breaking the spherical symmetry. Bondi accretion also makes it very difficult to grow light seeds. We already hinted at this a bit. And this is because the Bondi accretion rate is proportional to the square of the black hole mass, so that it then automatically becomes very difficult to grow these light seeds in the early universe. Related, it also makes it very difficult to reproduce the observations of bright AGN in dwarf galaxies, because again, dwarf galaxies typically host intermediate mass black holes, which then also really struggle growing with the Bondi prescription. Another class of black holes that seems difficult to get to with Bondi is this dormant overmassive black hole that has been uncovered by JWST. And again, even when really pushing the parameters on the Bondi model, getting to something like this is very, very difficult because of the strong dependency on the black hole mass. So this has motivated people to explore prescriptions beyond Bondi. One model on the market is the torque-based accretion model, which essentially models the angular momentum transport and gas inflows from kiloparsec scales to deep inside the potential well of the galaxy. This is a model that has already been implemented in the SIMBA simulations and in high-resolution simulations, as in the original Hopkins and Cartet paper here from 2011, has been shown to be highly accurate, and in particular more accurate than Bondi in these scenarios that they present here. Another method is the accretion disk particle method, where you also track not just the properties of the black hole, but also the properties of the unresolved accretion disk surrounding the black hole. And this is something that I will get back to later. So as part of LTU, Jan Berger has now also worked on implementing the torque-limited accretion model within our scheme. And there are a couple of main takeaways here. So the first one being that, unsurprisingly, with the torque-limited accretion, the black holes grow a lot earlier. So you can see here the black hole mass versus redshift, and the black hole accretion rate versus redshift, and the Eddington fraction versus redshift. And here the TNG comparison model is the red one. And then Jan has tested several implementations of the torque-limited accretion model. But for all of these variations, the black hole growth is much more efficient at high redshift, but then at later times is overtaken by TNG. And this has consequences for star formation. So if we look here at the black hole mass-stellar mass relation, we can see that it has intrinsically different shape from TNG. So you can see here TNG, the early growth is inhibited, and then you get a steeper relation, and then in the high mass end, again, you get something shallower as the more efficient AGN feedback kicks in. Whereas with the torque-limited accretion, you get a much steadier slope. And this then, of course, unsurprisingly affects star formation. So here you have the stellar mass-halo mass relation, and TNG, again here in red, very effectively suppresses this high mass end, whereas we struggle to do this with the torque-limited accretion model. And Jan has explored even more variants than the one shown here. And this really turns out to be a very difficult problem just by replacing the accretion model alone. And it really shows that because everything is so interconnected, you can't just switch out the accretion model. Once you've changed your accretion philosophy, you likely also need to update the feedback model to still be able to reproduce this stellar mass-halo mass relation as well as the gas fractions. And this leads me to another idea that has been developed by Rainer Weinberger. So he has developed a highly flexible, so-called dynamical accretion model. And the idea here really is that you have a kind of sinc particle-based prescription that is then limited by the freefall time. So you accrete the mass within the kernel on the timescale of the freefall time. And then he also has a modified implementation of this, where he implements an accretion disk that basically acts as a reservoir so that you have sort of delayed accretion. And this highly flexible model, Rainer found that he is able to calibrate the parameters of this model to match all major observables. And it is an interesting and also complementary approach to Bondi, as it is quite flexible and doesn't carry the strong dependency on the black hole mass. Then finally, for the accretion, I would also like to present the accretion disk particle method, which is something close to my heart. Of course, many other groups that I had on the earlier slide also work on this. But the main philosophy here of the accretion disk particle method, as I already mentioned, is that you don't just model the black hole particle and its mass, which is what almost all cosmological simulations do, but you also model the unresolved accretion disk, which is tracked together with the black hole particle. And this then allows you to also model the angular momentum transport through this black hole accretion disk particle. So you can track also the disk angular momentum, in addition, of course, to the disk mass, as well as the black hole spin. So rather than one variable, you're now keeping track of 4 variables. And the way that you evolve these, I will just give an example based on the mass evolution, because this is a lot simpler than the angular momentum evolution. But philosophically, the angular momentum evolution is very similar. So let's just think about how you involve the disk mass. So the way that this whole scheme is coupled to the hydrosolver is via the mass inflow rate and the angular momentum inflow rate. So you measure both of these at the scale of the outer accretion disk, and then the mass flux gets added to your subgrid disk. So the subgrid disk mass increases because of the external inflows, and it decreases because of the accretion onto the black hole. And the black hole mass is also quite easy to track. It increases because of accretion corrected for by the radiative efficiency. And you might also note that these accretion rates are not necessarily the same. And this is to account, for example, for wind loss in the disk. And yeah, then like I said, the inflow rate you can get quite straightforwardly from the hydrosolver. And then the accretion rate and the radiative efficiency is usually then just obtained from an analytical disk model. And the standard choice for most of the accretion disk particle implementation is the Shakura-Zunyaev thin alpha disk. And that is because that is the only global analytical solution for accretion disks on the market. But this model, if you're an accretion disk expert, you would say, oh, this is definitely wrong. If you're a bit more lenient, you could say, okay, this is probably a good approximation for the radiatively efficient regime. But once we go into the radiatively inefficient regime at either very low or very super Eddington fractions, this is definitely no longer accurate. And this is where our unified accretion disk particle method comes in. So we developed this model further so that it can change the disk state from a thin disk at high Eddington fractions to a so-called arduous flow, so a thick disk at low Eddington fractions, with a smooth transition between these regimes via a truncated disk. And I just told you that there isn't an analytical model, so you might wonder how this model then works. And the answer is many different ingredients. So for the arduous flow, you still have the self-similar ADAF or arduous theory that you can apply here. The only problem, of course, with self-similar solutions is that they break down at the boundaries. So anywhere where we needed to inform the model in terms of boundary values, we had to take input from GRR-MHD simulations, so general relativistic radiation magnetohydrodynamic simulations. In particular, from these simulations, we obtained fitting functions for the radiative efficiency, for the spin-up function of the black hole, so how the black hole spin is affected by accretion, and also for the disk precession behavior. And then we put all of this together to come up with this unified model. And we're currently testing this in IDS galaxy simulations. We already have a paper out where I put the reference here, where we're testing it in where we tested it in Sephtet cores and supermassive black hole binaries. But yeah, the next step really is now to put this all together. And there are also various other groups that are working on combining these next generation black hole models with multi-phase ISM models. So I've created a little collage here, especially since there's involvement also from LTU members in some of these. And the idea here really from most of these is to use low-mass galaxies as a laboratory for the black hole ISM interaction, because in dwarf galaxies or in high redshift galaxies, it is much easier to obtain high resolution and to then faithfully model these phenomena. And it's really, really interesting because, for example, it also shows here in this paper by Shin et al. And other papers have found similar points that this cold disk in the center of the galaxy around the black hole can be persistent and survive, and that the relation between what you would obtain from a disk-based scheme and a Bondi-based scheme isn't straightforward. So there isn't just a constant scale factor that you can apply, because really these accretion disk schemes behave very differently. To be able to port this now to the large cosmological volumes, because again, as I said earlier, this is where we ultimately want to get to though, we need to adapt the scheme because it requires incredibly high resolution. For all of these calculations that I just showed you earlier to be accurate, you have to resolve the mass inflow rate and the angular momentum inflow rate at the scale of the outer accretion disk, because you want to be confident that this mass and this angular momentum will actually reach the disk. We're talking here typically, full disclosure, about 10 to the minus 2 parsecs. So for cosmological simulations, again, that is not the resolution requirement that you want to hear. So, so this is why we've also been working on a machine learning accelerated framework. This is super early days, and I'm mainly actually just putting it up here to get ideas on how to do it better. But in the first iteration, we just used a summed multi-layer perceptron, where essentially all of the surrounding neighboring cells are being trained on the same MLP, and they all feed in the distance, the velocity, their mass, their density, and their temperature. And this is then being used to evaluate the mass inflow rate. And we've trained and validated this on dwarf zoom-in simulations, which within the small parameter space that we were investigating actually worked surprisingly well. And now the next step, of course, is to apply this to a much broader population of galaxies, and to also tackle the small challenge of the angular momentum inflow prediction. All right, this then takes me to the fourth and final challenge, the black hole feedback. So here there is even more road mapping required. So I already mentioned these different regimes, so the radiatively inefficient and the radiatively efficient regime. These are also the kind of interesting regimes when you develop your feedback model. And the Black Hole Working Group has been developing new models for both this radiatively inefficient regime, which you might have also heard of as the so-called radio mode, and the radiatively efficient regime, which is also often referred to as the quasar mode. So you can see here this really nice cartoon from this review by Harrison and Ramos Almeida. And in the radiatively inefficient regime, you expect more of this thick disk, possibly a truncated configuration, strong jets, whereas in the radiatively efficient regime, you might still have a jet, possibly weaker, and radiation plays a much bigger role. How this is typically implemented in cosmological simulations, I'm going to discuss here using the example of illustrious TNG, as this is often our reference simulation. And the way that it works here is that at low accretion rates, you have the kinetic mode, where kinetic energy is distributed via kicks in random directions. And at high accretion rates, you have the so-called thermal mode, where you inject isotropically and continuously thermal energy into the surrounding gas cells. Now, this is our starting point, and we've been working on adapting both of these aspects. So one project here that I will talk about is the Mistral model, which is where Marion Farsi has implemented radiatively efficient winds, so a quasar wind feedback mode. And then also Arkenstone black holes, where James Sullivan has been working on implementing jets based on this Arkenstone model that you already heard about yesterday from the ISM working group. And then we've also been working on running detailed wind simulations to better understand the coupling of the feedback with the multi-phase ISM. And we've also been developing new numerical techniques, in particular these cyclic zooms or multi-zone zooms, to think about how to recouple what we find out from these extreme zoom-in simulations that I described earlier. And then, of course, at the end of the day, we want to package all of this as subgrid models, so also thinking more about these GRMHD-inspired subgrid models, just like we did for accretion. But first of all, I'm going to focus on Mistral. So one of the motivations for Mistral was that there are various observations of powerful winds or outflows in massive galaxies at high redshift. However, with the standard TNG thermal mode, which tends to be dominant at high redshift, mainly just because you tend to be in this higher accretion regime at high redshift, you actually, as you can see here in this idealized simulation, wouldn't create these powerful outflows. So one of the questions that motivated Mistral was, do we need to revise our models of AGN feedback at high redshift? And here's a video of the same simulation, but now with the Mistral model for AGN winds that was implemented by Marion. And the way that this model works is that you now have an episodic injection of momentum, either aligned or anti-aligned to the angular momentum vector of the central gas. And again, Marion implemented various versions of this model that we don't have time to go through now. But the most successful one is the so-called Mistral stochastic, where a few cells are kicked stochastically at a set wind velocity VW. And Marion has also tested this in cosmological zoom-in simulations and found really intriguingly that one of the things that Mistral can achieve is early quenching. So quenching of massive galaxies at relatively high redshifts, which is also really interesting in the JWST context, where people have been suggesting that there could be a puzzlingly high number density of quiescent galaxies at high redshifts. So perhaps Mistral is one of the ingredients that could help towards running cosmological simulations that agree with these observational hints. And Marine Prunier has also been working on applying the Mistral feedback model to the galaxy cluster regime. So she has rerun one zoom-in halo with a halo mass of approximately 10 to the 14, and then investigated the X-ray cavities that are produced by this feedback model. And here in this plot, you can see the projected cavity area as a function of projected cavity distance from the supermassive black hole. And the Mistral points are here in purple, the TNG cluster simulations are in blue, and the Hyena simulations are in green. And then there are also some of the observations here as the triangles. And what is really interesting to observe is that Mistral, for some of the snapshots, so you have to remember this is a bit different from TNG cluster in this, these points are many snapshots rather than many clusters. But for some of these snapshots, you get these really extreme cavities. So this is definitely a constraint, perhaps. It still needs to be better understood. And of course, we need a larger sample of cluster zoom-ins with Mistral to understand if this is like typical Mistral behavior, I guess, and if this is something that could be used to further constrain this model. So I mentioned that we've also been running detailed wind simulations. So this is something that's been led by Samuel Ward and Tiago Costa. And in particular, they've been investigating this mixed phase in this really detailed simulations of the wind ISM interaction. And they found, focusing on kind of X-ray predictions, that this X-ray emission should be detectable on kiloparsec scales in local quasars with Chandra or access, and that we can really use this X-ray emission as a probe of mixing layers in kind of AGN wind ISM interactions. Okay, this concludes the radiatively efficient / quasar mode part. We move to part 2, modeling AGN jets. And this is really the multi-scale challenge ad extremum. So this is a slide that was kindly contributed by Minghao, which I absolutely love. So he made this nice comparison where here there's an observed jet that spans a scale of 5 megaparsecs. And if you compare the size of that jet to the size of the event horizon of the black hole where it originates from, it would be the same as comparing the distance from New York City to LA to the width of the human hair. So this is what we're dealing with here. And various people in the group have been working very hard at grappling with this challenge. So, and before I offer solutions, there are more bad news, which is that there are even more challenges for quasi-Lagrangian codes and jets. So we already heard this yesterday, that Lagrangian, or in our case quasi-Lagrangian codes, can struggle to resolve high specific energy winds, and this is because the resolution follows the density. So that a high specific energy wind will automatically have less resolution, and the space where this high resolution wind, or in our case jet, is supposed to couple in, i.e. in the CGM, will also suffer from lower resolution. So this is where the Arkenstone method comes in, which was developed here by Matthew Smith for stellar feedback, but we're now saying, like, okay, we also suffer from these rapid radiative losses, so let's take this and adopt it for our black hole feedback modeling. And this is exactly what James Sullivan has been doing. So he's been adopting the stellar feedback method to the black hole feedback scenario. So instead of the star-forming cells, it's now the active black holes that are being flagged as launch sites. And then you create and launch the wind particles according to the black hole feedback framework. And again, these wind particles, just like in standard Mistral, are hydrodecoupled at launch and then recouple within the CGM. And James has been running some idealized simulations to test his new implementation, which are already very promising and show that he is able to regulate the star formation rates with his Arkenstone BH implementation. And the next steps are now, first of all, to run zoom-in simulations, again, bringing the cosmological context back into the game. And of course, also, we heard about the Arkenstone cold implementation, to also transfer that to the black hole scenario, and then ultimately to inform the mass loading, the energy loading, etc. of these winds, to tie this in with the unified accretion disk model and couple everything together. And then last but not least, it will also be really interesting to compare this Arkenstone black hole implementation and the Mistral implementation. So that's another thing on our to-do list for the next few months. For the jets, again, we've also been performing detailed simulations of the jet ISM interaction. This is being led by Olga Borodina, and she has several fascinating results that can't possibly all fit into this one slide. But just to give a few highlights. So she found that the launch jets can get trapped in the turbulent ISM, and the details of this really depend on the ISM structure, which of course we can't resolve in the large volume cosmological simulation. And fascinatingly, as you can see here in this video, you can see kind of here the jet spreading in red, and you can also see the very irregular propagation and how it actually propagates around these cold clouds, which interestingly still manage to survive. So in the context of thinking, can feedback and accretion be sustained simultaneously? The survival of the cold clouds is really fascinating. Okay. This now takes me to the last part, which is zooming in on black holes. So I mentioned to you guys earlier that we also follow the approach of just zooming in as close as we can get to faithfully represent the physics happening close to the black hole and the accretion disk. And this is an approach that within the working group has been led by Minghao Guo. And here there are some really nice simulations where you can see how you zoom from galaxy scales all the way down to close to the event horizon scale. So here you are at 10 gravitational radii. So this is really impressive. But of course, you can't just zoom in. You also have to zoom back out. And one really important point, going back to the previous slide, is that this is not just about spatial scales. It's also about time scales. So when you're going down to these tiny scales, you're talking about time scales of days. So if you keep just zooming in and cranking up the resolution, you're almost starting to freeze time. And you really need to think about how do these processes that are launched on these small scales that you're now resolving affect the much larger time steps and much larger structures. And this is something that Minghao has also been worried about. He said, actually, I should be launching from here the relativistic jet and then figuring out how that affects these larger scales. And how do we tackle this? So there are several approaches, nicely summarized in this table. So one is the direct approach, where essentially you very faithfully model the accretion disk and the outflows around it, typically with GRMHD simulations. You will probably do a really good job at resolving the inflows or the outflows, but going to large scales is going to be an issue here. The second approach then, of course, is the zoom-in approach that we've just been talking about. And again, you're going to do a great job with your boundary conditions. In fact, that's probably more faithful than if you're starting off from some kind of torus scenario. But you can't really recouple that outflow. So that is difficult. And now the silver bullet is the multi-zone or the cyclic zooms, where you're hoping to take all three of these boxes by essentially circumventing these time step issues that the first two approaches suffer from. How do you do this? So you have in your simulation an active region and a masked region. And what you then essentially do is that the masked region periodically changes as a function of time, so that you resolve these really small scale structures and then start masking these regions again. You can investigate the large scale effects and then zoom in again. So you're constantly zooming in and zooming out. The nice thing is the speed up. So if you were hoping to do all of this ab initio and go from event horizon scales to galaxy scales, then you're looking of running your simulation for a lovely 50 years perhaps. With Minghao's cyclic zoom approach, you're shortening this to 5 days, which of course is a very attractive speed up. The question that you might then have on your minds is this numerically robust? And Minghao would probably say, as far as I know, yes. So he has carried out various tests, and I'm just showing you one here from this idealized simulation. And what is really interesting when you look at the movie, I'm going to play it again, but first I'm going to tell you what to look at. So look both at the large-scale structure and at the small-scale structure. Here in the top row, you've got a standard simulation where just everything is constantly resolved. And here you've got the cyclic zoom. And if you look at the small-scale structure, then you can see how basically you have the small-scale structure depicted and coarse-grained, constantly kind of on-off. Whereas the large-scale structure actually visually and also quantitatively, if you check out Minghao's paper, is very robust. So this is a really promising approach that we're now also hoping to part towards cosmological simulations. And I'm almost towards the end of my time, so I'm just going to briefly mention the synergies that we have with other working groups and projects. So the ISM working group has already been mentioned several times, and of course it's crucial here that we carefully coordinate our feedback models, thinking about all of the interdependencies and degeneracies. The cosmological simulation group is another very obvious partner. Of course, we need good black hole models to produce realistic outcomes in cosmological simulations. We've also been working with the synthetic observations group, and in particular this week at the pre-meeting, we had a really nice session where we've now made plans to use luminosity functions as a new discriminator for the models that we're developing. And we're also working with the AFM working group, thinking about these machine learning accelerated subgrid models as a new tool that I mentioned. We're working with Borg, in particular, thinking about setting up these constrained initial conditions for cluster zooms from Uli's talk. Cosmological surveys, we had the wonderful talk this morning, so I don't really need to mention it more, but there's a very obvious overlap with AGN feedback. And of course, really any other working group that requires detailed comparisons with observations, particularly with red galaxies and their evolution. So that takes me to my summary slide. The black hole working group has now developed new models for all 4 challenges: seeding, dynamics, accretion, and feedback. And we have also developed novel numerical methods for addressing the multi-scale challenge and for comparing with observations. So the next step now, in fact for the first few months, are to combine these different strands of the black hole models and hopefully also the new ISM models and run some first multi-zoom production runs, hopefully by the end of 2025. And this will then also allow us to test the interplay with the new star formation and stellar feedback models and to create the high-fidelity mock observations in collaboration with SynSops. Thanks.